Assalamu alaikum and hello everyone. So this is PAT 257 lecture 3 part 1. So before we start, let us do a bit of revision on what we have done so far. For lecture 2, we calculated the active force. We calculated the active force per unit length of the wall using Rankin's lateral earth pressure theory. Okay, remember? And for this lecture, I'm going to show you guys how to do the same. To calculate the active force, PA, but this time we are going to use the Coulomb's lateral earth pressure theory. All right, so maybe all of you guys now are wondering what's the difference between Rankin's and Coulomb's theory. So the difference is, for Rankin, the one that we did in lecture 2, Rankin assumed that this retaining wall is frictionless, meaning there is no friction between the retaining wall and the soil. Okay, so that's Rankin. But for Coulomb, Coulomb took into consideration the friction between the wall and the soil back here. Okay, and that friction angle is denoted as this one, delta prime. Okay, delta prime is the wall friction angle. It is between this wall and the soil at the back. All right, I repeat myself. For Rankin's theory, Rankin assumed the retaining wall to be frictionless, no friction between the wall and the soil. But for Coulomb, the one that we will do today, or in this lecture, Coulomb took into consideration the wall friction angle, which is the friction between the wall and the soil. All right, so as I said to you before, if you are interested in knowing more about how the formulas used in this lecture were derived, then you can refer to the textbook, which is Principles of Geotechnical Engineering, 9th edition, or any other textbook. Or you can Google, or you can also text me so that we can discuss further, inshallah. All right, so let's start. Let's go straight to the point. Those with the book, it is example 13.11, this one. All right, as you can see, this is the retaining wall, and the height is 4 meters. Everything else is given, unit weight. This is soil friction angle. This is wall friction angle, alpha and theta. So you have to calculate PA, as well as the direction and the location of PA. All right. Okay, so now this is unit weight 15. Okay, this is friction angle, and then this is soil friction angle. What about the alpha? Where is alpha? What is alpha actually? Okay, so alpha is here. Okay, alpha, I hope you can see, this is alpha. This is the location of your alpha, and then in this case it is 10 degree. So for theta it is this one. Okay, the sloping of the, okay, this is theta. Okay, so this is theta, which is the slope of the retaining wall at the back, while alpha is the slope of the backfill. Okay, all right, so how to do this? So let's start just like what we did before. Okay, I hope you can see what I'm going to write. All right, so let's start at Z equals to 0 meter. So what is Z again? Z is the depth from the ground surface. So this is your Z, okay? The depth from the measured from the ground surface. All right, so when Z is 0 meter, So our vertical effective stress is obviously 0, isn't it? Kilonewton per meter square. We don't have any surcharge, okay? See, we don't have any surcharge. All right, so vertical effective stress equals to 0. So therefore, our Coulomb's active earth pressure is also 0 kilonewton per meter square. And the pore water pressure is obviously 0 as well, kilonewton per meter square. Okay, we don't have any, since this soil, the unit weight given is not saturated, and there is no groundwater. Groundwater table is not involved in this task, so there is no pore water pressure. There is no pressure coming from the pore water acting on the wall. All right, so this is 0. All right, done. So for the second one, at z equals to 4 meter. Okay, so vertical effective stress equals to gamma h. That's what we did before. Gamma is 15 times 4. Therefore, vertical effective stress equals to 60 kilonewton per meter square. Am I right? Okay, let me check. Okay, please bear with me. Just want to double check. 15 times 4, right, 60. All right, so what about the Coulomb's active earth pressure? Equals to Ka times vertical effective stress, where Ka equals to, this formula is very long formula, is really long. Not really, it's long. Okay. Okay, I'll show you the formula. It is this one for Coulomb. I hope you can see. This is the formula. All right, and actually we can make our life much easier by using the table, the one that I gave to you guys in PDF format. Basically, that table, it uses the same formula, but they calculated all the values already. Okay, so we can use straight away, so we can save more time and make our life much more easier. All right, but either you use that table or you use this formula, the value of K must be the same. All right, if it's not the same, you have to calculate it again. All right, so for Ka, I repeat myself, for Ka, for Coulomb's active earth pressure coefficient, you can use the formula, which is long. It is this one. Sorry, yeah, this one. Or we can make our life much easier by using the table. But which table to use? Okay. All right, which table to use? There are 3 tables, if you notice. The first one is this one, table 13.4. All right, so are we going to use this one? All right, let's look. For theta, for this table, theta must be 0 and alpha must be 0 as well. All right, but in our case, our theta is not 0, our theta is 5 and our alpha is 10. So this is a no. We cannot use this table 13.4. all right. Okay, what about this one? Table 13.5. Can we use this? Okay, I want you all to look at this note here. See, delta prime, which is the wall friction angle, it is 2/3 from the soil friction angle. All right. Okay, let's see. I'm sorry if you get a bit confused. All right, so delta prime, this is table 13.5, okay, equals to 2/3 of the soil friction angle. Is it true? Okay, 2/3 times our soil friction angle is 30 degrees. So we'll get 20, isn't it? So 20 degrees. Is it true? No, it's not, because our wall friction angle is 15 degree. So we cannot use table 13.5. This is also a no. All right. So obviously, we can use table 13.6, right? But just to check, okay, let's do the note again. So this is the wall friction angle equals to soil friction angle divided by 2. What is our wall friction angle? So wall friction angle is 15 degree equals to 30 divided by 2. 30 is the soil friction angle. This is equals to 15 degree. So the same, isn't it? 15, 15. So we can use table 13.6. Now how to use it? Okay, how to use it? You look at the first column. This is alpha, and the second column is soil friction angle. Sorry. So our alpha is what? 10, isn't it? So we have 0, 5. So go to the next page. 10. All right, we'll stop here. 10. Okay, this is us. I'm gonna use pencil. Sorry. All right, so this is us, 10. So what about our soil friction angle? Soil friction angle is 30. We are here. And then theta. What is our theta? Theta is 5. So this is us. So therefore, the value of your Ka is this one, isn't it? 0.3872. So Ka is 0.3872. This is from table 13.6. okay, but if you want to use the long formula just now, you should or you must get the same answer, the same value. If not, then you have to calculate again. All right, so let's get back to our task here. So now the active earth pressure equals to 0.3872 times 60, isn't it? The vertical effective stress. So this equals to, please bear with me, 23.23 kilonewton per meter square. Okay, what about the pore pressure? Pore pressure, we don't have any pore pressure, okay, because the groundwater table is way below the retaining wall. So pore water pressure is also 0 kilonewton per meter square. So now what we have to do is we have to draw the graph, remember? But in this case, we just need to draw one graph, just this graph, the active earth pressure, Coulomb's active earth pressure, since pore water pressure is 0, just to make things faster. All right, so I'm sorry, I don't use ruler here. Okay, so this is, do the axis. This is active earth pressure. Unit is kilonewton per meter square. And the one pointing downward is the Z. This is in meter. All right, so this is 0. Our retaining wall is 4 meter. And basically this is the value. Okay, here is 23.23. Okay, so then to calculate PA equals to what? Remember, PA equals to the area under the graph. Okay, so we just have one area over here. So half times the width of this triangle, 23.23 times the height, which is 4. Therefore, our PA equals to, please bear with me, 46.46 kilonewton per meter. Right. So the first task is done. So the active force per unit length of the wall is 46.46 kilonewton per meter. So this is done. So today I'm going to use a pink highlight. Okay, there. This is Done. So what's next? All right, I hope you're with me. I hope I'm not too fast. All right, so the second one is the direction and location of the resultant force. So we go to the location first, since it is straightforward. So Z, basically we want to find the location of the resultant force. So how to calculate? It should be 1/3 from the height of the wall, isn't it? So therefore 1/3 out of 4. So the location of the resultant is 1.33 meter. This is measured from the bottom of the wall. All right, so this is the location. All right, so this is the location. So what about direction? So okay, can you see? All right, so what about for direction? Direction is, okay, let me draw this again. Okay guys, so now I'm going to show you how to draw the direction of our PA. All right, so okay, this is the figure just now. This is the retaining wall. I draw this again so you can see better. All right, the force in Coulomb's case is, you notice this, the surface of the retaining wall at the back. All right, so how to draw the direction? Okay, how to show the direction is, first you draw a normal line to, it is normal, so that it is normal to the surface of the wall back here. What is normal line? Normal line means when you draw it, it will make a 90 degree angle to the wall surface. So I'm going to draw my normal line here. Okay, so approximately, okay, see, this is my normal line. Okay, and now see, this is my normal line, and now it is making a 90 degree with the wall surface. All right, approximately 90. Okay, so this is my normal line, normal. All right, okay, so the direction of our PA is here. This is your PA. This is your PA, and this angle here equals to the wall friction angle, which is 15 degree. So this is the direction of our PA. All right, remember, I repeat, first to show the direction of our PA, you draw a normal line. A normal line means it will make a 90 degree to the surface of the wall. Okay, 90 degree, and then from this line, PA is located at an angle of 15 degree, which is equal to the value of the wall friction angle, this value. Okay, so this is our PA. And to summarize, this is the direction of our PA, and this is located at, okay, I'm going to use a different color. This is located at the one that you calculated just now. Sorry. This is this PA. How to draw this? I'm sorry. Okay. This PA is located at 1.33 meter. Okay. 1.33 meter measured from the bottom of the wall, and the value of our PA is the one that we calculated just now, which is 46.46 kilonewton per meter. All right, so we're done with this PA, and we're done with the location. It is located at 1.33 meter measured from the bottom of the wall, and this is the direction of your PA. All right. So we are done with lecture 3 part 1. All right, and then we will continue with lecture 3 part 2. So in part 2, basically we will apply all the knowledge that we have so far to check the stability of our retaining wall. Okay, so all right, that's it for now. Thank you for listening.